So again, we're going to start from the beginning when we talked about Gauss's law. Remind you guys that this symbol here, phi, is electric flux. Very good. And we have these random other symbols that are super very important that I will explain a little bit more once we get to them. Okay. Ultimately, Gauss's law isn't necessarily about flux. All right. So I've been talking a lot about flux, but Gauss's law isn't about flux. Gauss's law is about electric field, and the relationship that he came up with was more, the important part of it was more this part, this second part of the equation, all right? In fact, flux is really not that important. I'll ask you some questions about flux today, but ultimately, the reason why we're doing this is to find the electric field of complicated objects. Okay? So far, so good? Okay. So let's move on. So I want to come back to this slide here, and I was talking to you guys about how flux changes based on a surface. So maybe some review question. If I were to have my surface, which direction is my surface facing? Vector direction. If I have this, it's facing upwards because you have to imagine that every surface has a perpendicular vector unit pointing pointing away from the surface, just like that. Okay. And if I had a round surface like this, right, at this point here, where is its surface vector pointing? Upward, yeah, because there's a tangent line along the surface, and it's going to be perpendicular to that point. Okay? And so, if I were to go right there, where would the surface vector be? Okay? That. And so therefore, there's a surface vector that's perpendicular to the surface that goes literally all the way around this surface. Okay? And as long as the electric field is parallel to this area, the surface area vector, then you can just do a multiplication of the magnitudes of the electric field and of area. So I'm going to write that here. Nope, that's not what I want. So we can say that the surface area, sorry, the flux is equal to the magnitude of the electric field multiplied by the magnitude of the area and multiplied by the cosine of the angle between those two. Okay? And that's all the definition of a dot product. So a dot product is you're taking two vectors and you multiply them along this certain angle. Okay? And so if there was a 0-degree angle between the electric field and the area, then you would have the cosine of 0 degrees would be 1, and so you'd have your flux would be at its maximum possible based on those two, based on the electric field and based on the area. If the angle was less than, or not less than, but if it was between 0 and 90, the electric field would be, sorry, the electric flux. So the electric flux would be 0 or positive or maximum. It would be positive, but not maximum. Okay, if the angle is between 0 and 90. If the angle is 90, then the cosine of 90 is 0, and therefore there is no flux, and that situation is represented. This field line going in this direction, there would be no electric field going through the window surface that you established. Now this is important because we have to, if we want to estimate things, if we want to estimate the electric field of objects and do it in a convenient mathematical way and not have to do really complicated triple integrals and all that stuff, we have to choose an electric field that'll make the math simple for us, all right? And so this is an example of that. So imagine that you have a wire, right? And this is just a straight wire like that, and it's charged. Don't think of it as having any thickness if you think that's too much to think about right now. Think of it as just a long straight wire. And you have a toilet paper roll around it. Okay, we spoke about a toilet paper roll. So basically, you finish your toilet paper, all you have left is that thin cardboard thing, hollow. There's the surface area, but there isn't a cap on either end, and it's hollow all the way inside. Okay, so I put my my charged wire. Now, if I were to cut my wire, just like that, right? And I looked at inside of it, I would see this, right? This is what a wire looks like if you cut it. And this is a charged wire, so it's got a positive charge all along the inside. And if you were to look at it that way, what would the electric field lines look like? Yeah? Towards exterior, radially outward. Okay, so there you go. There's your electric field lines. Yeah, Mark? At the, yeah, you're right, there would be at the ends of the wire. Okay, yeah. But I'm looking at a section in the middle only.
Alright. So like, for example, like if you pass a wire, therefore there's electric field all around the wire.
I see what you're saying. So if you were to look at a wire like this, yeah.
There's still all around.
Good question.
Or it's
Yes.
like only like narrow at the end.
There is still an electric. Yeah. Okay. So there's a wire here, and it's a finite length wire, which means that all along there's going to be let's say it's positively charged. All along, it's going to be charged radially outwards. Okay. Except at the ends, you no longer can follow those rules. So the ends of it will start to look like this. Okay. So this makes it so that we can't really closely approximate what's going on at the ends. So what we do is we focus on the part that we can focus on, and that's the middle part where everything is just radially outward. Okay, Sean, you got a question? That's the wire so far. Okay, I haven't gotten to the toilet paper yet. Exactly, just looking at it from a different perspective. Okay? All right, so now let's look at the toilet paper roll. Here's my toilet paper roll on the right, so TP. And this toilet paper roll has a surface all along the exterior. So at any given point, we should be able to determine what its area vector is. So let's say at this point, on the right of this TP roll, what is the area vector direction? Yeah? Towards the right. Okay? And then all along, there is going to be area vectors that are pointing outwards. Yep. Why not tangent to the circle? Yeah. Because the tangent of the circle is the surface, and if that were the surface, if that was the sheet of paper, the line that I just drew, then therefore the area vector is pointing outwards. Okay, Melanie? So if you look at like you saw me when I rolled that thing up? Yeah, so if I were to roll it up, the paper roll, the area vector is the surface, at that point, the area vector is there. And all along the surface, it's going to be pointing outward, no matter where you are along the length, but along the side, it's going to be right there. The area vector. All right, so it's perfect. This is amazing because I chose this toilet paper shape to put around my wire because at every single point, what is the angle created between the electric field and the area? 0 at every single point. All right, so then if I were to draw it like this, there's my wire, there's my toilet paper roll. At any point that I pick along this wire, whoops, At any point along this wire, the electric field is going to go outwards. And check it out. It's going into the same direction as that area. If I choose this electric field line, there is an area vector in that direction. If I choose this electric field line, there's an area vector in that direction. All right, so at every single point along my wire, my electric field is parallel to my area. So I can say that at this point, if I put the this toilet paper roll over the wire, the flux is always going to just simply be equal to E times A. And that's just some regular multiplication, not a dot product, because the cosine at any point is always going to be zero. And so at any point, if I take it at every single point along this toilet paper roll, my dot product is going to give me at a cosine angle of 0, and therefore it's just going to be E times A. Right? And that's perfect because I chose that surface. I chose to use a toilet paper roll. I could have used a much more complicated way to find the flux. Okay, and I'll tell you what I mean by that once I get to the next example. Yeah. So flux is not a vector. Okay. So the multiplication of whether I multiply them or not, the resulting answer is not a vector. Okay? So here you can use the magnet. All right, I'm going to come back to this slide in a second. I want to do this one quick. I have right at the middle here, a spherical charge. Just this part, just this tan part is a spherical charge. You can consider it to be a point charge, or you can consider it to be a spherical charge, right? It doesn't matter. It applies for both cases. All right, so here's my spherical point charge. I'm going to switch to red so that you guys can see better. There's my spherical point charge. And as long as something is charged, there are electric field lines coming out of it or coming into it. If it's a positive charge, what do the electric field lines look like? Radially away from it, okay? So away from it is important, but it's also important to mention that it's going radially outwards. So there's my electric field lines, all right? And imagine this is a sphere, so there's also electric field lines coming towards you and going away from you, all right? And now I'm going to say, pick a surface that you're going to put around this sphere so that the electric field lines coming out of that charge will always be at a 0-degree angle with the electric fields coming out, or at a 0-degree angle with the area vectors of this shape that you choose. A sphere, exactly. So if I take this sphere here, okay, at any single point, check it out. I have an area vector that's parallel to my electric field vector. So the angle created between this electric field and this area is 0. Okay? So again, I can say that in this case, that the flux is simply equal to E times A. And again, I want to remind you that we chose to pick that surface, all right? And if we were to look at it differently, all right, we're going to get up with the same result. I'm going to just look at this a little bit differently. I'm going to say, let's take this small area here, dA, all right? I'm going to add them all up to get the total flux. So I'm going to get total flux by doing something called a surface integral, all right? And that's what this symbol means. It's an integral symbol with a circle in it, which means that it's a surface integral. You don't need to know how to do this mathematically. You just need to understand what this is conceptually. It's an addition of everything along a surface, okay? Of the electric field dot product of dA. And what's cool about this is if I were to measure the electric field at any point along this sphere, is it going to be the same or not? What's the distance from the center of the sphere at right here? R. What about here? What about here? What is the charge that I'm comparing to at the plus? So let's call this capital Q. If I choose to find the electric field here, what's the Q? Capital Q, capital Q, capital Q, capital Q, capital Q. So at any point here, the electric field is constant. So I can even take that out of the integral and say E surface integral of dA. You want to close that? And so what's the surface integral of that small dA? If I add up all the little areas along this whole surface, what am I going to get? Yeah? It would be, well, forget about the limits, but conceptually, if I add up all the little areas, I'm going to get, Johnny? 4 pi r squared in the case of a circle in a sphere, but in concept, it's the total area. So E times A. And that's exactly what we said before. See how much simpler our math became because we chose a surface that makes sense? If I chose to put like a cylinder around this point charge, I couldn't tell you that at every point the electric field is the same. I couldn't tell you that the electric flux is going to be the same at every point. But because we chose what we call this Gaussian surface to be conveniently equal in terms of its surface area vector all around, then it makes the math that much easier. Okay, and this is going to be very important when we move on to know what a Gaussian surface is. We'll do some practice. Yeah. Exactly. Yeah. All right. Gauss didn't just come up with this flux, as I mentioned. He also came up with this second part of this equation. So here it is. This is the main expression of Gauss's law. And what he says is that, yes, flux is equal to this electric field multiplied or dot product of the area, right? But it's also proportional. I'm not gonna prove this to you guys, though there are YouTube videos that you can go to if you want to see the proof for this, that the charge inside this Gaussian surface divided by some constant epsilon naught will also give you that same flux. Okay, so let me just define what epsilon naught is for you guys. So epsilon naught is a constant, 8.85 times 10 to the negative 12. Can't remember the units. You can look that up. And it's also, who remembers seeing this symbol when we were doing Coulomb's law? Yeah? What was it again? Do you guys remember what its relationship was with something else? Yeah? Exactly, exactly. So I'm going to take what you said and just refine it a little bit. 1 over 4 pi epsilon naught is the same thing as writing k. Okay, and k you guys are familiar with, that's the 9 times 10 to the 9. That's that constant. Epsilon naught has a very complicated name. You guys know what that name is? It's called permittivity of free space. How did you not know that? That's equal to epsilon naught. if I were to rearrange this, because it might be useful later, I can also say that if I just move the k there and the epsilon not there, I'm allowed to do that algebraically. I can say that 1 over 4 pi k is equal to epsilon naught. And that might be convenient if you only remember one of the constants and you forgot what the other one is, so you're going to fish it around for it and you try to figure it out. You can do that. Okay? Again, I want to draw your attention to this. Gauss says that the electric flux is equal to the charge inside divided by charge inside the Gaussian surface divided by a constant. What variables define flux in that relationship? Yeah? Not k. There's no, I mean, k is a constant, so that's not a variable. Just q. That's it. Just q. All right? So if I were to go back now to this slide here, right? And here, look, I took a fantastic Gaussian surface. I took a circle called S1. And I'm saying, okay, I took a Gaussian surface and the charge inside is Q. Tell me what the flux is coming out of this perfect Gaussian surface. You guys would say, well, that's easy. That's just Q over epsilon naught. So the flux is just Q inside divided by epsilon naught. So what's the Q inside this Gaussian surface? Capital Q. What's the, if I took this weird shape S2 Gaussian surface, medium-sized Gaussian surface, what is the flux coming out of that Gaussian surface? The same thing. The Q inside over epsilon naught. And what about, so this is for S1, this is for S2, and for S3, same thing. The flux is always the same, and it's only proportional to the charge inside of it. Okay? As long as this surface is closed, that's the only requirement, right? So if and only if. Have you ever read this abbreviation before? This is if and only if. Okay? If and only if Gaussian surface is a closed surface. All right. Let's move forward and let's try to do some examples. Here's one. What is the flux coming out of my weird Gaussian surface? My Gaussian surface is this weird shape there. What is the flux coming out of it? Want to try? Plus 2 only? What's inside my Gaussian surface?
Or you have
Exactly. All right. So I add up all my charges. In this case, it's minus 3 plus minus 3 plus 2, which is, oh, sorry, minus 3 minus 5 plus 2 is minus 6 over epsilon naught. There's my flux. Minus 6 coulombs, yeah. And so I have a number now that represents flux. Simple enough? Okay, in this case, I have this surface 1, and there's a charge positive Q inside. What's the flux of this surface 1? Yep. Yeah, it's just plus Q over epsilon naught. That's the flux for S1. What would you say the flux is for S2? Exactly. Negative Q over epsilon naught. And this is for S2. Let me ask you guys a question here. What do you notice about the lines, the electric field lines, coming out of this surface? Yeah? They follow the direction of the arrows? Okay, yeah, they follow the direction of the arrows. What direction is this? Are they all outwards or are they all inwards? All outwards. If they were all inwards, like this one, it would be negative. So there's a negative flux, there's a positive flux. All right? What about for this Gaussian surface here? Are the arrows flowing in or out? Both. So anything that flows in flows out. So what is the net flux on this? Zero. What's the charge inside the Gaussian surface? Zero. So the flux is zero. What's the flux around this big surface here? I call this big pan area S4. What would be the flux for that? Zero. Why? Exactly. The same amount flows in that flows out. What's the charge inside this surface? Maybe think of it that way. It's plus Q minus Q, zero. So the flux of S4, even though it has charges in it, the flux is zero because the charges cancel each other out. Very good. I have a question for you guys. There's 5 examples here. Tell me which one of these examples has the highest flux. And then tell me the ones that are go lower between us. So basically, place them in decreasing order of flux. The first one being the highest flux, the last one being the lowest flux. How do you determine flux? Are you guys awake? Oh yeah? Very good. Why did you think that B and E are equal? Absolutely it. Okay, the radius or the size of the Gaussian surface doesn't matter. For flux, the only thing that matters is the charge inside. Promise? So our Gaussian surface is a square, or a squiggly line, or a circle. It doesn't matter. What's the charge inside? But we're not talking about electric field right now. We're talking about, if you were talking about electric field, then you'd be right. But we're talking about flux only, all right? And if we go back, here it is. The only thing you care about for flux is charge enclosed divided by epsilon naught. Yeah? Yeah. Yeah, you can use that too. It's going to be different for, so that's the thing. So if you go to a square, what's the angle coming out? So let's do that. There's the electric field coming out radially outwards. And at this point, the surface is that way. At this point, the surface is that way. At that point, the surface is that way. So if I were to calculate the flux that way, it would be way too complicated. Yeah, because the angle of the electric field is going to change every single time, and the angle of the area is going to change only 4 times. And so to be able to do that using calculus is just way too difficult. Okay, so the area vectors on this case are like that, like that, like that. So using that method is not recommended here. All right, one more thing, and we're going to do some problems. I'm going to go back to this little example right here, okay? In fact, I'm going to erase this. You'll still have it later, but I'm going to erase this for now. Oh, actually, you know what I'm going to do? Cool. Yeah, I'm going to add a slide. All right, so I'm going to say that I have some point charge Q. We'll call that plus Q, but we'll call it Q nonetheless. It doesn't really matter what that charge is. All right, now I want to determine at some distance r what the electric field is. Okay. So far, you guys have a tool to use to be able to measure this. Right? So you have a charge, you have a radius. The electric field is kq over r squared. Boom, done. But something had to lead to that, right? So Gauss said, all right, if you take that point at a distance r from a point charge, and you took any other point at a distance r, and you took any point at a distance r, then you could create what you call a Gaussian surface that passes through all of these points r. Okay, so there's my Gaussian surface. And now if I make a Gaussian surface, and it's very convenient because all the electric field lines coming out of Q are going to be parallel to all the surface area vectors coming out of that Gaussian surface, I can say that E times A is true. I don't need to do the cosine angle, I don't need to do dot product, because again, I chose a Gaussian surface such that every single time my electric field comes out of the charge, it's parallel to the area vector coming out of my surface. And that is equal to Q inside divided by epsilon naught. Great. What's the area of my sphere? I'm asking you to tell me right now, what is the area of the sphere? I don't know why I put an equal sign there. Yeah? Area of a sphere, not volume of a sphere. Area of a sphere. Okay? Yeah, 4 pi r squared. So E multiplied by 4 pi r squared is equal to Q inside over epsilon naught. And if I want to know what the electric field is at that point r, then let's just isolate electric field, and that's going to be Q enclosed divided by 4 pi epsilon naught r squared. Right? And what was 1 over 4 pi epsilon naught squared again? K. So E is equal to KQ inside over r squared. Yeah. Which ones? Yeah, like the weird squiggly ones, like this one, for example. So it all depends on what my question is. My question when I was looking at this was, well, what's the flux? When I did this one, I asked you, what is the electric field? Okay, so if I'm asking for electric field, then you have to solve for electric field. If I'm asking you for flux, then you have to solve for flux. two different things. How about for a cube? If I drew a cube, Gaussian surface, and I put a charge Q inside, what would be the flux coming out of the cube? Yeah? I'm asking for the flux, not the, what's that? Yeah. Yeah. How do you calculate it? Yep. The question is flux, not electric field, flux. Yep. Q over epsilon naught. Simple. I could be a bit more tricky though, and I can say, okay, that's the total flux coming out of the cube. Therefore, what would you say the flux is coming out of only one out of the 6 faces of the cube? Exactly. Then it would be divided by 6. So the flux for one face is equal to Q over epsilon naught multiplied by 1 over 6. I can only do this, I can only divide by 6 and get a nice number because I have, what kind of shape is that? It's a cube, and therefore, what's special about a cube? It's symmetrical, or what can you say about the faces? Not that they're parallel, that's not important. Area. Okay, so if I were to use this same problem and say prism, and inside of it, and I put this charge, and I asked you what the flux was coming out of only one of the faces, then you wouldn't be able to calculate it because the flux wouldn't be the same for all faces. The flux, the total flux coming out of it would be the same as if you were to put a cube. The total flux would be the same as if you were to put it in a sphere, but the flux coming out of one surface would not be calculatable. Yeah. You could do it with a ratio, yeah. If it's a rectangular prism, but if I made like a non-perfect polygon, then it wouldn't work. Yeah.
If you're able to calculate the total area, then you divide the flux by the total area, and find the area that
You can do that.
Place,
Yeah, you can do that. Yeah. You'd have to know the parameter of every single line. Right? Okay, yeah, it works. Okay. So far, so good. Without even reading the options, you should be able to answer this question. What is the flux of this Gaussian surface? 0. Why? Flux lines are coming in and out. Another reason, someone else? You guys are forgetting the key point to Gauss's law, Bronwyn. Exactly, the charge inside is 0. Don't forget that, okay? Q inside over epsilon naught. If the Q inside is 0, it's 0. Okay? Okay. So we're going to do this one together, and then I'm going to ask you guys to do the next few in groups. So what is the electric flux around an imaginary sphere of radius r if only one charge Q is at the center of the sphere? The question is asking about what? What are we asking about? Flux. Please don't get that confused with electric field. So what would be the electric flux coming out of this? Mark? Yep. Okay. And now the second question is asking you about what? How does the electric field vary for an imaginary sphere? What am I asking about? Now I'm asking about electric field, right? And we derived the expression for this already, right? It's a little point charge with a sphere around it. What is going to be the electric field? Yeah, kq over r squared. And we got that using Gauss's law. All right, so here's what I want you guys to do. Please discuss this. I like it that you guys talk. It really does help you guys learn. I did it with you guys last class, and I thought it worked well, and I want you guys to do it again. I understand that it's awkward for some of you to force yourself to be social or whatnot, but it really does help you to understand these things. Okay? So do example 2. Tell me when you have an answer. I'll come. You can talk about it with me. You can ask me questions, whatever you want. Let's do this for at least 20 minutes, okay? So, if I were to just do this one, most of you are done this one, you guys got some good answers. But there is a very fast and easy way of doing this, all right? So if I had drawn, if I'm using Gauss's law, that's the whole point of all, to use Gauss's law. If I were to draw a Gaussian surface, and remember, I choose where my Gaussian surface is. If I chose the Gaussian surface right there, all right, see, look how I drew a Gaussian surface inside. What could you tell me about the electric field inside, or the flux inside? So the flux is equal to, what is it? 0, but why? What are the two parts of this? I'm just going to draw this. E times A is equal to Q inside over epsilon naught. How did you guys know that my flux was 0? All right? The charge on the inside of my Gaussian surface is 0, right? So therefore, if this is 0, is the area of my Gaussian surface 0? No, right? So this is a 0, so this side is 0. My A is not a 0 because my Gaussian surface has an area. What's my E then? If this both multiplied together has to be equal to 0, what could you say about E? It has to be 0, okay? It's the only choice. So if I chose my Gaussian surface anywhere the inside of this, because the charge enclosed is always going to be 0, then the electric field inside automatically has to be 0. And that's the same thing for the outside. If I chose the Gaussian surface outside, right, and now my Gaussian surface has a radius r, whoops, my Gaussian surface here has a radius r, I can say that my flux is equal to my electric field times the area of my Gaussian surface, which is 4 pi r squared, is equal to Q inside over epsilon naught. And the electric field on the outside of my sphere is going to be kq over r squared, just like we did before. So in fact, whether my charge is a sphere, whether my charge is a hollow sphere, if my charge is a solid sphere, if my charge is a point charge, doesn't matter. As long as it's a sphere shape, on the outside of that sphere, you can treat that object as a point charge and use kq over r squared. And it's the distance from the center of the sphere, not from the surface of my object, right? So this is not r here. My r is not this distance. That's not r. R really is the radius of my Gaussian surface. Okay, the distance from the center of the charge. And now if I were to graph this now, at a distance 0 from the center, what is my electric field? What is my electric field right there? 0. What is my electric field right now? Keep telling me what they are. Okay, here? Very big, maximum. And then now as I get further and further away, is it getting lower and lower or higher and higher? Lower and lower. So if I were to break my graph up into two sections, First being the part inside my sphere up until the radius r, my electric field is 0, okay? And then afterwards it gets really high and then comes downwards, like that, okay? So that's how electric field varies as a function of the radius outside. Now, I'm not going to be super picky about this because you didn't learn it. If I were to do the same thing about radius, to find the inside is actually a bit more complicated. I've been okay with you guys telling me that it's 0, but there is actually a different way of calculating this. I'm okay with you guys assuming it's 0, okay? It's not 0 though. In reality, it's something like this, okay? And then afterwards, it decreases. And this proportionality here, this is the important part. Your proportionality here is 1 over r squared, while the proportionality here is just 1 over r. Okay, and you get this because this is kq over r squared, and this is kq over r. That's how you know that. I want you to use that method, drawing yourself an imaginary Gaussian surface in different parts for the next few problems, because that's going to make a lot easier. Okay? All right, keep working. You can take a break at any point. At 11, this class goes up until what time? 12, right? At 11:15, I'm going to ask everyone to start working on the problem set. is dark conducting stuff. So what's important what's out here, or about here, a sharp inside is going to be so that really and the charge controls the body. Guys, I have a question for you that's going to help you with some of these problems. If I had, first of all, remind me again, what's the difference between a conductor and an insulator, aka a non-conductor? What's the difference between a conductor and a non-conductor? Conductor allows electron flow, or electrons are allowed to move freely. If I have a solid conductor, not hollow, solid conductor, all right, and the electrons are allowed to move freely, where are they going to go to be the most happy? Do electrons like each other? Eh? No, electrons hate each other. So what electrons are going to do to make themselves happy is they're going to spread out as much as you can. If you're an electron and everyone's spreading out, what is the place along the solid sphere where they're the most spread out? Marco, Josh, I'm speaking, and this is Mark. If the charges are spreading out, where are they going to spread out to in order to have the most space between them? The surface. So if you have a hollow conducting sphere or a solid conducting sphere, it don't matter. The charges are all on the outside. Okay? Another? Okay. Guys, everyone now stop and take a 5-minute break. Come back in 5 minutes.